All right, welcome back as we talk about diffusion mass transfer. So, diffusion primarily occurs at the electrode surface, and if we have enough supporting electrolyte, then for the analyte, it can be the dominant form of mass transfer, which is really handy because then we can define our current from our analyte, with a pretty simple mathematical expression where we have, the number of electrons exchanged, Faraday's constant, the area, diffusivity, and then our gradient of concentration. That's something that we can solve with differential equations. So, that's one reason why supporting electrolyte is incredibly important if you want to be doing electroanalytical chemistry. So, let's define what the diffusivity is, though. Just, an overview. It's how far things are moving in your solution given a certain amount of time. And this term here, this comes from something called the random walk model that can be fairly easily derived. And what it tells you is that the diffusivity tells us here we have our change in x. This is about how far things are moving in our solution, and then over 2t. If we do a unit conversion on this, then we're left with centimeters squared per second, and that's the primary unit for diffusivity. The Stokes-Einstein equation, this is a really handy thing that can actually allow us to predict diffusivities. And what it uses is the Boltzmann's constant, it uses temperature, the viscosity of our solution, and then the radius of our species of interest. So if we do an order of magnitude analysis on this to see, hey, do we get close to literature values? Well, we can plug in Boltzmann's constant as 10 to the minus 23 joules per Kelvin. Let's say we're running at room temperature, so 300 Kelvin. We can approximate this. 6 pi is 10. The viscosity is 10 to the minus 3 Pascal seconds. That's the approximate viscosity of water. And then let's say that our analyte is an angstrom across. So if we do this, then we get 10 to the minus 9 meters squared per second. And when we do a unit conversion to centimeters squared per second, then we're left with 10 to the minus 5 centimeters squared per second, which, this is just spot on. This is right around where many of the diffusivities of species in room temperature water lies. So, I mentioned that we can actually solve these equations using differential equations. And Fick's laws are an integral part of that. So the first, Fick's first law just describes the flux, the diffusivity, and the gradient of concentration, how these fit together. The second law that we need for solving these differential equations is based off of our mass balance equation. So we're going to say that, hey, accumulation is equal of a species is equal to the generation of that species inside a volume plus, whatever we're putting, however much of that we're putting into the volume and however much we're taking out. We can rearrange. We can plug in, our actual mathematical terms. So here we have, the change in our concentration over time. And then here we have our flux representing the in and out terms. And then we say, we're not worried about reactions going on. We're just talking about mass transport. And so we say that there's no generation. We rearrange. And when we rearrange, then we're left with Fick's second law. Now, you'll notice that we go from this nabla term to a nabla square term. And this nabla square term, it's called the Laplacian operator. And I just want to talk about that really quick. Here we have it written out for planar, cylindrical, and spherical coordinate systems, but only in the most simple of their possible forms. So here with planar, we're only assuming that there's movement in x. And so we're neglecting y and z. For cylindrical, we're neglecting z and phi. And for spherical, we're neglecting phi and theta. Now, the other part of the puzzle that we need to solve our differential equations is the boundary and initial conditions. Here are some of the most common boundary and initial conditions. These are, the semi-infinite condition, where we say that far away from the electrode, that's what this x going to infinity means, our concentrations at any time are going to be equal to, the bulk initial concentrations, what we started off with. Then we need to describe what's going on at the electrode surface. So we could write out the Nernst equation, or we could write out this balance. And often a few of these are used together. But this boundary condition is saying that, pretty much whatever we're making as far as the oxidized species go, the opposite is happening to the reduced species, because they're converting into each other. And then we can assume some initial conditions. The most common one is to assume a flat concentration profile. So we're saying everywhere in the solution at time 0, we have the same concentration. Now, like I said, these are only good for soluble-soluble. And, if you're doing something like deposition where you have an insoluble reduced product, then it's going to be completely different. And, semi-infinite might not be an appropriate boundary condition if you have electrodes that are really close to each other. So in that case, you would have to make changes to these boundary and initial conditions. Let's talk about limiting current. So when do we consider our reactions to be mass transfer limited? And the answer is that we assume that happens when the concentration of our analyte is practically 0 at our electrode. Mathematically, we can write this out here where you can see clearly we're going to have the most extreme values of current when this term, which represents the concentration of the oxidized species at the electrode, or right here for the reduced species, when that term is 0, this whole expression has its maximum value. The H here stands, of course, for the mass transfer coefficient. Now we can write out our expression for the current itself, using our flux ideas. This is, of course, Fick's first law. And then we can, approximate this delta C here. And if we combine this current term and this limiting current term, then we can come up with an expression for the mass transfer coefficient, where we say that it's approximately equal to the diffusivity of species J over the diffusion layer thickness. So here we have a little definition of the diffusion layer thickness. The diffusion layer thickness is, conceptually, how far out into the solution is diffusion changing things. And mathematically, how we usually define it is we draw a tangent line, and where that tangent line intersects with the bulk concentration level, we say that's the diffusion layer thickness. Okay, so here's a question or two for you that I'd like you to answer. The questions are for 2 electrodes with the same area, so the same surface area. Would you expect to have more current from diffusion with linear diffusion or radial diffusion? And then why would you expect that? So go ahead and pause the video and I'll give you an answer in a few seconds. Okay, so we would expect more current to come from a species that is diffusing radially. And here's the reason why. So if we're expecting only planar or linear diffusion, then the current always is accessing, the same area or volume from the solution. So as time goes on, we're not accessing more and more of the solution. But with radial diffusion, you'll notice as time goes on and the diffusion layer continues to grow larger and larger, which will lead to more current at our electrode. Okay, Well, we hope you'll join us for our next mini video as we talk about convection in electrochemistry.